Hi Bharat,
Hello,
how are you?
I'm good. How are you?
Fine,
Long
surviving.
time.
Yeah, yeah. So you are in Netherlands?
Yes, I am.
Good. How are things over there now? Now I think restrictions have been removed, right? Most of the COVID restrictions.
Yeah. So, like last Friday, they removed pretty much all the restrictions except like mask in bus or like public transport.
One, masks have to stay for some time in any sensible
Yeah.
place.
So, yeah, they opened the offices also, so which is good. Like at least you get to see people.
Good, good.
Previously, I think they opened for like a month or so in October, but then they had to close everything again because the cases just skyrocketed.
Good. Anyway, you should be setting up your talk now.
Yeah, just I will
Yeah,
start with
so it's working, right? Yeah. Huh. Mute mic.
give me one moment.
Okay, so Archit, who is going to introduce Bharat, Dr. Bharat is here. Archit, can you switch on your camera? Okay, so it's 5. So we'll start this. I will invite Archit from MS-20 to introduce our next speaker, Dr. Bharat Kumar Gehlot, and then we'll directly start for the talk. Archit, to you.
Hello, good evening, everyone. I am Archit Kulkarni from MS-20 batch, ISR Mohali. I welcome you all to the second session of the Symposium by Astronomy Club. So for the first speaker for our today's second session is Dr. Bharat Kumar Gehlot, who is an ISR Mohali graduate from MS-09 batch. Dr. Bharat graduated from ISR Mohali in 2014, majoring in physics. He completed his PhD at Captain Institute of the University of Groningen, Netherlands, which is research focusing on investigation of observational challenges in 21 centimeter experiments probing the cosmic dawn using the state-of-the-art LOFAR telescope. He continued his research as postdoctoral researcher at the School of Earth and Space Exploration at Arizona State University, working with the next generation HERA MWA EDGES telescope and simulation of these instruments to further understand the challenges in the 21 centimeter cosmology. He is currently continuing his postdoctoral research at Captain Institute and leading the AARTAFSC Cosmic Explorer project. In today's talk, he will briefly update the current status of the ongoing 21 centimeter cosmology experiments and discuss results from various studies he conducted to investigate and mitigate the challenges in 21 centimeter cosmology experiments. It is our great pleasure to have him with us today. With that, I will hand over it to Dr. Bharat. Thank you.
Thanks for the nice introduction. So hi everyone. Today I'm going to talk about the quest for the cosmic 21 centimeter signal. So of the neutral hydrogen. So this is basically part of the cosmology. So 21 centimeter cosmology, where we are trying to look at the first giga years of the universe and to understand the astrophysics and the physical processes that govern the structure formation during that time. So I will try to keep my talk a bit simple so that like everyone understands. And please feel free to interrupt me if you have any questions in the meantime. So you can see the presentation. So
Yes, we can. Yeah,
Yeah, we can.
we can see.
okay, so let's begin. So I'll start with the basic chronology of the universe. So starting from the beginning. So in the paradigm of the Big Bang cosmology, after the Big Bang, the universe was basically hot, dense, and opaque. So it was just like a soup of subatomic particles and photons where they they would just interact with each other, and because of like high scattering cross section between the photons and the particles, the light could not escape. So that's why it was opaque. But as the universe expanded after that, so it started to cool down because of the adiabatic expansion, and the density started decreasing. So as the universe cooled down further, like so roughly around, let's say 400,000 years, the universe cooled down sufficiently, like around to 3000 kelvins. And at that time point, the protons, or like electrons and neutrons, they combine to form the neutral hydrogen and helium. So this is what we call the epoch of recombination. And at this point, because the density was low and the universe temperature like went down, the radiation or the photons were not anymore coupled to these electrons and to the atoms, and so they just escaped in the void. And that point of time in the history of the universe, we call it as the epoch of recombination. So the radiation that escaped from that last scattering surface, that is can be measured nowadays as the cosmic microwave background. So it redshifted to the microwave band of the electromagnetic spectrum. Now, at that point, the epoch of recombination ushered the universe into the cosmic dark ages. So during the cosmic dark ages, the universe was basically transparent, and it was cold. There were no light, no radiation sources. So it was dark, and it was also neutral because just there was only neutral hydrogen and helium, pretty much. And but as the universe evolved further, the small perturbations in this and the matter density, matter I mean like dark matter and baryonic matter density, so these perturbations actually grew gravitation under gravitational instability, and eventually formed first nonlinear structures of dark matter halos. So these were the main potential wells where all the first generation of stars and black holes formed. So this point of time, we call it as the cosmic dawn, when basically when the first generation of stars forms, or the luminous objects. These in these halos itself, the first galaxies, mini quasars also formed. So since, as I mentioned, that all the hydrogen in the universe was neutral at that point, except from these from the regions around these stars. So the radiation from these stars, like ultraviolet radiation and the X-ray radiation from the X-ray emitting objects, actually started heating the neutral gas in the surrounding intergalactic medium and started ionizing this neutral hydrogen. And there was a point when these ionized regions, or we call them ionizing bubbles, started to merge together, and this process continued until all the neutral hydrogen in the intergalactic medium actually went from being neutral to completely ionized. So this phase transition from of the universe from being neutral to ionized is we call it as epoch of reionization. And in present day universe, the IgM is ionized. The only neutral hydrogen we observe are present in galaxies or damp Lyman alpha systems. So
Hello.
why do we need to study the universe's first billion years? So the cosmic microwave background, we can actually provides a snapshot of the moment when the last scattering surface happened, after the epoch of recombination. So basically 400,000 years old. So this has been measured very well. So the first CMB measurement came in like late in 60s by Arno Penzias and Roger Wilson, and they also got a Nobel for it. And later, there were like a couple of space missions. For example, there was a COBE space mission, a WMAP space mission, and Planck. So these space missions have like very well, very accurately measured the CMB as well as the fluctuations in the CMB temperature. And on the other hand, the present day universe is also very well studied. So using observational stars, galaxies, galaxy clusters with different kinds of instrument can be radio,
Hello.
Infrared,
Uh,
and
Hello.
ultraviolet. Yeah.
Sir, sorry to interrupt, but your voice is very unclear. Can you try to fix that maybe? Because it's very hard to.
Just give me, is it like low or is it high or is it cracked?
No, it's like it's very low actually.
Okay, let me try to increase the volume. Is it better now?
Yeah, sir. Thank you.
Okay, so okay, so let's continue. So where was I? Yeah. So as I was saying, the present day universe is also very well studied using different instruments, can optical telescopes, radio telescopes, red telescopes, and all. And we have studied like a lot. For example, galaxies, galaxy structures, galaxy clusters, evolution and kinematics of galaxies, star formation, properties of stars, interstellar medium, intergalactic medium, even circumgalactic medium, etc. However, there is this like time period in the history of universe, starting from dark ages to all the way to the end of reionization, which is largely unexplored. So basically, we don't have a lot of information from these epochs. And observing these epochs can actually answer very important questions about how the universe evolved from being like completely dark and neutral to what we see today. These questions can be like when these dark ages actually ended, and when did it transition to cosmic dawn, and when the reionization completely finished, what were the properties of this first generation of stars, how did the first galaxies form. So a lot of information you can answer just by observing and probing these epochs. So it's basically like tracing a movie of evolving baryonic as well as dark matter structures during this first billion years. Okay, so let's continue. My slide stopped working. Yeah. So this here I just summarize what we can actually probe by looking at different epochs in the first billion years. So probing the dark ages, we can give us information about dark matter, power spectrum evolution as a function of time or redshift. We can study more dark matter annihilation physics as well as baryonic bulk flows. Cosmic dawn is very interesting, where the first stars appear. So mostly we think these are population 3 stars, which are only made of hydrogen, hydrogen-rich stars, not like stars we see in the present universe, as well as black holes. The Lyman alpha radiation field that actually eventually started to ionize the neutral hydrogen. The first X-ray heating sources are mostly black holes or the AGNs, etc. The impact of these baryonic bulk flows on the structure formation. And then during the reionization, we can actually study the reionization by stars or mini quasars. So there's still an open question then which objects actually reionized the universe. Was it the stars or were they the mini quasars? And then the transition from the population 3 stars to population 2 stars, feedback in the IGM because of supernova remnants, etc. And then galaxy formation as well as the emergence of the present universe. So, and then the later is the post-ionization era, where we can probe the baryon acoustic oscillations, which can provide a handle on the dark energy equation of state, as well as intensity mapping that tells us about the formation of a large-scale structure evolution. And there are like tons of experiments that are aiming to do this. So mostly cosmic dawn and reionization and dark ages are kind of the instruments that are aiming to measure signal from these epochs are radio instruments. There are some instruments, for example, JWST, ELT, etc. These are infrared and visible telescopes that can go into reionization, but not too far. Definitely not the dark ages, because there are no luminous objects. Okay, so moving on, what do we already know about these epochs? So there are like bunch of indirect probe as well as some rare detection of the objects that has provided some information. So one of them is called Thomson scattering of the CMB photons. So this cosmic microwave background photons actually get scattered due to by the electrons in the intergalactic medium that actually leads to a net polarization. So this happens only because there is a quadruple anisotropy in the background itself. If the background signal were completely isotropic, that means if the signal were like same coming from all directions, then we would not see any net polarization. But since there is a directionality in it, that ends up with a net polarization. So this tells us that the reionization epoch happened at peak around redshift of 8. But this is a very, how do you say, an indirect probe, that what we measure is an integrated effect instead of something which gives us a evolution information. Because of it, there are very limited information that we can obtain from this. And then there is another probe, which is the observations of high redshift quasars and gamma ray bursts. So we actually look at the absorption spectrum of these, for example, especially the Lyman alpha line. So since so we basically observe these quasars which were present during the reionization as the light travels towards the us, so it gets redshifted, and at different redshifts, the intervening gas can actually cause absorptions in the spectrum. For example, this is an example here. Let's say the quasar is at certain redshift, and it because of what we are observing it now, the Lyman alpha line gets redshifted to a certain wavelength. But as the light passes through different regions of the universe, and the intervening gas, or like for example, if there is a galaxy in the line of sight, you see a strong absorption of Lyman alpha at a different redshift corresponding to the redshift of the galaxy, and then any hydrogen clouds, etc., will cause absorption. However, if the quasar is located at reionization redshift, that is like during the time when the reionization was happening, then we actually see a Gunn-Peterson trough. So this is basically a complete absence of any emission, because the Lyman alpha line is optically thick. That means that if it passes through a cloud of gas, it gets absorbed very quickly, and the transmitted light is very the fraction of transmitted light is extremely small. So because of this, we actually see these troughs, and these troughs are like helpful to understand when the reionization actually ended. Now, the problem with high redshift quasar measurements are that we cannot look deeper into the reionization epoch, because as the neutral hydrogen density increases, you don't you stop seeing these quasars. And then there is another probe which is just looking at the high redshift galaxies and the Lyman alpha emitters. So there's you can make correlation between the number density of these emitters as well as with the redshift, and that tells you that as the redshift increases, the number density of these Lyman alpha emitters goes down. You can also make inferences based on the star formation rates. So although the star formation rate of these high redshift galaxies are high, but the number is so low that there are still not enough photons to ionize the universe. So you can actually get some information, but it's not like you can still there are still many questions that left unanswered. So what do you do? So in that case, you go to the radio frequencies. So you look at the neutral hydrogen brightness temperature. So it has been shown like for almost 70 years that the 21 centimeter transition is an excellent tracer of the neutral hydrogen in the universe. So first time a Dutch astronomer, I forgot his first name, the last name is Van der Hulst. So he observed the 21 centimeter transition from our own galaxy, and afterwards it became a very prominent probe of neutral hydrogen in the nearby galaxies, and you can study a lot of physics because of that. And then over like last I think 2 decades ago, people have found out that we can actually observe this brightness temperature over cosmic time, because the line is optically thin, so it does not get absorbed as quickly compared to the Lyman alpha. So we can actually look back into the past and then just measuring the neutral hydrogen distribution can provide ton of information about the universe. For example, this is the brightness temperature equation that this is the brightness temperature that you can measure. And there are like so many things you can infer from this equation. For example, there's ionization fraction that as a function of redshift that tells you that how the reionization continue during the epoch of reionization. There is cosmology, so you can get information about cosmology, color parameters during that time. There's you can study about gas of astrophysics, and then there's also you can study peculiar velocity and bulk flows. So the H1 brightness temperature is nothing but hyperfine transition of neutral hydrogen, and this has been like very well studied and like observed in lab as well. So let's look at how this gas actually evolves during the cosmic time. So I'll just show a quick animation. So this is a video of a cube, of a cosmic cube, where you have there are a bunch of sources, luminous sources, and they start ionizing the hydrogen. And let's see how it evolves. It's not. There is something wrong with this animation. This is not good. Not supposed to work. Okay, I'm really sorry that this doesn't seem to be working. Okay, so essentially this is basically, this video shows that how these luminous objects and galaxies start to ionize the neutral universe.
Hello. Sir, can you please try switching from pointer to cursor? Then maybe you should get it.
Yeah, I actually did, but it doesn't seem to be working. Let me try one more. Okay, it's working now. Okay. So you can see the black part was actually neutral hydrogen, and then these glowing parts are the radiation that is ionizing this hydrogen, and eventually you will see that all the hydrogen is actually ionized by the end of reionization. These regions of ionized gas are also called reionizing, these ionized bubbles in the 21st century cosmology jargon. Yeah. So you can see now that there are many more stars, and all the hydrogen actually transition from neutral to ionized. So it started from let's say early cosmic dawn, and then end up and stop at the reionization, at the end of reionization. So now the next part is, how do we actually measure this redshifted 21 centimeter transition of neutral hydrogen? So what we can measure are, in principle, there are three things. One is you can actually use telescopes to just directly image the hydrogen at that time. So since the transition happens at 1.4 gigahertz, so it is redshifted now. So depending on the observing frequencies, you can actually say that, okay, I'm observing the hydrogen at this particular frequency, this particular redshift, and that provides the evolution of the observing it with function of redshift provides a picture of the evolving universe. Then there is another probe. It's called the global 21 centimeter signal. So in this one, this probe is basically averaging the redshifted signal, measuring the redshifted signal, but as the average of the whole sky. So this one is the easiest, as we say, but it has the least amount of information that we can get. And then there is another one, which is the measuring the spatial fluctuation in the 21 centimeter brightness temperature as a function of redshift. And from this, you can actually, if you measure these different, if you measure the signal using these different probes, you can actually use astrophysical models to get the fit for the and constrain the parameters as you want. So let's dive into a bit more. So the global 21 centimeter signal, as I said, is basically measurement of the sky average brightness temperature, and you measure it as a function of a redshift. It only constrains the global properties, but the thing is that it requires relatively simple instruments. So mostly these single element radiometers or single element telescopes, which are really sensitive and have very nice and clean frequency response. And then the next is to measure another one is to measure the spatial or spectral 21 centimeter brightness temperature fluctuations. So this you can measure using statistical techniques. We call this power spectrum, bispectrum, 1 or 2 point statistics of this brightness temperature fluctuations, and you can study it as the study it like with respect to the redshift, so you can get the picture of the evolving universe. It does require arrays of a large number of antennas which are cross-correlated. So these are also known as interferometers. And then there is a third way, which is the direct imaging or tomography techniques. So it retains everything. There is all the information, but it is not possible at all with any current generation instruments. We have hopes that the upcoming square kilometer array may be able to do it, but that has to be seen. So this is out of the picture for at least a decade now. So therefore, like all the experiments that have been running for last decade are focused on either measuring the global signal or the spatial fluctuations of the signal. Okay, so let's first talk about the global 21 centimeter signal experiments. So these are fairly simple experiments. So they observe the radio sky with a highly custom designed instrument. So the instrument has been usually designed to be as achromatic as possible, so that it does not add its own response onto the measured signal. And fairly simple receiver system that there is a calibration chain, you amplify the signal, and then finally you look at the spectrum. So the spectrum is a function of frequency and time, and what you look is at the sky temperature. So this is a typical average sky temperature as function of frequency. And the next part is to remove any contamination from the galaxy and the ionosphere and whatnot. And finally, in the residual spectrum, you can actually search for these 21 centimeter signals. So there was a detection recently, a claim detection. So I'll talk about it later. So there are a bunch of experiments that are actually working to measure this global 21 centimeter signal. So there is EDGES in Western Australia, SARAS-3 in India, REACH is upcoming instrument in South Africa, LEIDA in United States is still going on, it's in Owens Valley. PRISM is another upcoming instrument on Marion Island, so this is like extremely radiofied site. And then MIST in another upcoming instrument in Canada and Chile. So they will be like two sister instruments at different locations on Earth. Okay, so these experiments are just are searching for the global 21 centimeter signal. So far, we have seen results from EDGES and SARAS, which are like which have like kind of stirred a lot of debate in the community, but other instruments are still ongoing. Now let's move to the next class of experiments, which are the experiments that are measuring the fluctuations. So these are interferometers. So interferometers are basically these are arrays of many antennas, and they work on a principle of classical phase interferometry. So this is, I think you have probably studied in optics course or in high school, Young's double slit experiment. So this is basically a bunch of these Young double slit interferometers. Why do we need an interferometer? So it allows you to achieve high resolution without building ginormous antennas. For example, if you want to achieve a degree resolution of a degree in the sky, you would need to have an antenna of 300 meters. But with interferometer, you can still place two antennas which are 10 kilometers or like 3 kilometers apart, and you will achieve like a resolution of almost like a tenth of a degree. So basic principle is that if you have two antennas which are close enough, just like if the space between the slit is slow, you get a wide fringe on the sky. If you like keep move the antennas a bit far, the fringe pattern made by the source from the sky becomes narrow. So that means like a finer fringe pattern means that you achieve a higher resolution. With many antennas, this is how a fringe looks like. So this is what we also call as a point spread function. So it kind of tells you the resolution of the instrument. So this is a very interesting technique that was developed in late 70s, and then it's still being used. And now there have been like so many strides in this interferometry, and pretty much like all the radio instruments that are making cool images are interferometers. Even the Event Horizon Telescope is an interferometer, which made the image of the supermassive black hole. Okay, so how do these interferometers measure the signal? So you have like bunch of antennas on the ground. So you in the receiver, you get the signals from all these antennas, you amplify them, and then you correlate them. What is a correlation? Correlation is basically taking the Fourier transform of an antenna and then multiply of a signal from an antenna and then multiply the signal from a pair of two antennas, from a pair of antennas. This is what we call as correlations or visibilities. And these visibilities are in aperture space. And then if you want to make image, so if you Fourier transform these visibilities, you can actually get images of the sky. And from these visibilities, you can measure what we call a power spectrum. Power spectrum is basically representing power as a function of frequency and spatial frequency. So the key behind measuring separating the signal, what we want to measure, and the contaminations is their frequency behavior. So any signal, any foreground signal, for example, if it's a synchrotron signal, any contamination from our Milky Way or like these extragalactic sources at the same frequencies are expected to be smooth in frequency. So they tend to they limit themselves to on a certain range of spatial and spatial frequencies. And then we have instrumental response, which your instrument is chromatic and it behaves differently at different frequencies. So that can also corrupt the signal. So it also limits itself into certain region of the Fourier space. And then the signal is expected to be varying much faster than the instrument or the foregrounds. So each frequency corresponds to a slightly different redshift, basically a slightly different universe. So the signal varies rapidly as function of frequency, but we want to measure. So using this basic idea, we try to separate the signal. However, it has been not done yet. That I'll talk about why. So there are again so many experiments that are happening around the world to measure this redshifted signal from cosmic dawn and epoch of reionization. So there is LOFAR and ARTFAC in the Netherlands, MWA in Australia, HERA, which is a more recent one in South Africa, NENUPHAR in France, Owen's Very Long Wavelength Array in United States, and then the upcoming SKLO. Well, this is not just it. The next frontier is actually going to space, which is putting these global 21 centimeter instrument or interferometer on the lunar orbit or the far side of the moon. So there is NCLE. So this is Netherlands, China's low frequency explorer. It was launched in, I think, 2018. And they are basically studying so it's kind of a Pathfinder mission. So they are studying the feasibility of putting a more sensitive instrument in the lunar L2 orbit. There is also DAPPER. So this is a proposed mission. It's still it's still in design phase. The expected launch timeline is later this decade, and then this will be in a low lunar orbit. And then there is another instrument which is far side. So they want to place an interferometer on the far side of the moon. So this one will again, the timeline is also 2030s, sometime around that. So they are currently going through a design phase. But just to summarize the status of the 21 power spectrum experiments, so far there have been so many upper limits on the signal. That signal is always below this, but there has not been any significant detection. So you can see many results, but the actual signal that we want to measure is still order of around at least an order of magnitude lower than where we currently are. So this is an extremely steep task. I'll talk about why. And there have been it's not all bad. There have been some developments in last 3-4 years that in 2018, the Aegis group claimed that they detected this absorption feature in the global 21 centimeter profile. And this feature is expected to be caused by the first generation of stars during the cosmic dawn. However, the Saras-3 group in India, 2 months ago, they published a claim that the Aegis detection is not correct. Both instruments had there have been concerns who's true, who's not. So there was still it's in the gray area. We are not 100% sure whether either of them is correct. So there is a lot of follow-up that is required. But so far, I've told you that okay, there have been so many instruments. There have been claims that it has been detected or not detected. But why is it that it's so difficult? That's actually the scale of the problem. So there have been the signal we want to measure is extremely faint. We are talking about a level of few millikelvin. So just to provide a scale, the cosmic microwave background is around 3 Kelvin. So this is 3 orders of magnitude lower than the cosmic microwave background. So it's kind of like finding a needle in a haystack. And there are so many contaminations that actually distort this signal that you would like to measure. For example, there are astrophysical foregrounds that tend to be 4 to 5 orders of magnitude brighter than the signal itself. So these galactic foregrounds can be few Kelvin to few hundred Kelvin brighter. And as you go to higher and higher redshift, or if you want to measure signal from cosmic dawn, these foregrounds become way brighter. So going from few hundred to order of tens of thousands Kelvin bright. And then the Earth ionosphere, that also affects that distorts the incoming signal. There's also man-made radio frequency interference from mobiles, TV, radio, etc. On the top of that, there are also instrumental imperfections, data processing artifacts, and so on. So let's talk about this a bit. So astrophysical foregrounds are basically the galactic foreground emission or the extragalactic foreground emission, and so not or. So the contamination from Milky Way mostly coming in the form of synchrotron radiation or supernova remnants. Synchrotron field, it emits radiation, and this radiation is it's broadband. It's emitted in a range of radio frequencies, and it does not vary, and it varies very nicely, smoothly with frequency. There is extragalactic foreground emission. there's still like the mechanism is also like very similar, it's non-thermal, but these are coming from the point sources. So these are basically radio galaxies and cluster of galaxies. So you can see it in images, and also like high resolution, you can actually see these compact sources. So these are actually radio galaxies that we are seeing. There are ionospheric propagation effects. So as the radio wavefront passes through the ionosphere, so ionosphere is a layer of the Earth which contains the ionized plasma, which contains the plasma. So mostly like electrons. So as the wave passes through the ionosphere, it introduces fluctuations in the wavefront, and these fluctuations manifest as refractive effects or diffractive effects. That means like things won't appear at the same location as they are, or you will see a diffraction pattern around sources, etc. So this is a problem because this effect can actually mimic what we are trying to measure. And the other one is artificial radio interference that, of course, humans always cause problems. So there is you get interference from radios, television, mobile, air traffic control, even windmills and satellite communication. And these are usually narrowband, transient in nature. Again, they can also mimic something. They can also distort what we are trying to measure. They can mimic what we are trying to measure. And they sometimes that you can't even like do science if there's like too much RFI. So it's big. It's a really big problem. So that's why they decided to actually go to the moon where there is no RFI sources. Of course, on the back side, because on the front side, you will just like see our RFI from Earth. But on the back side, it's I think the most radiofied zone, at least in the Earth and Moon neighborhood. Okay, the next is the instrument itself. So no instrument is ideal. There have all the instruments have certain like issues. So for example, polarization leakage. So what is polarization leakage? That typically most of these receivers are designed to measure the two linear polarizations, but they are placed such that they look perfectly perpendicular, orthogonal if you are looking from zenith. But as you started to look from certain direction, they don't appear orthogonal anymore, and that causes a leakage of polarization. That means that if something is polarized, it can appear unpolarized, or if something is unpolarized, it can appear polarized. It's an apparent effect, or a geometric effect. There is also mutual coupling. What is mutual coupling? This is very interesting. So if you have like instruments which are more 3D, for example, if you have a bunch of dishes like this in Hera, you can actually have signals that actually bounce off like many antennas and then detected in a different antenna. This can cause like very interesting modulation in the frequency behavior of the instrument that affects our signal extraction process. There are also cable reflections that the signal going to the receiver can also get reflected within the cable because of the impedance matching. So, and then all the instruments have a chromatic response, that is like they respond to different frequencies differently. Now, most of my work have been like understanding these effects separately in different instruments, and it's very challenging task, which it involves a lot of signal processing and a lot of understanding of instrument, as well as the behavior of the astrophysical foregrounds and whatnot. So moving on, and so as I talked about that there was a detection in 2018, claimed detection in 2018 of the 21 centimeter absorption profile from the cosmic dawn. We actually, when that result was reported, it was a very unique result, because what they reported was something which we do not expect it. For example, the absorption they reported was much deeper than what we expect from simulations, or what we expect from the standard astrophysics. And it was also significantly wider. So this was very surprising. So there were like bunch of propositions that how do we explain this anomalous behavior. So there's some groups actually proposed very interesting models. So we call them exotic models. For example, one model that can explain this sort of behavior is that there is an interaction between the baryon and cold baryons and dark matter particles that eventually, that also cools the intergalactic medium, hence the absorption is deeper. Or there is like another population of sources, unknown sources, that can produce a much stronger radiation background, so your apparent absorption is deeper. So based on this, we actually proposed a project called ARTFA Cosmic Explorer. So this project aims to measure the 21 centimeter power spectrum at the redshift of that absorption profile. And this instrument uses a novel mode of the LOFAR. It's called ARTFA Quiet 3D Measure. So instead of looking at a small region of the sky, we look at the sky from like horizon to horizon. For example, this is one of the images that we made from the data. We published some results in 2020 that in a small chunk of data, we saw that the data becomes dominated by the instrumental noise at the level of 8 Kelvin. So if the signal we are trying to measure is below 8 Kelvin, so this is what an upper limit means. So very recently, I also got involved in in the instrument that is going to be placed on the moon. This is the far side instrument. So this instrument is actually a probe class concept. It's funded by NASA. The basic design will be having 128 non-collocated antennas. Non-collocated antennas means instead of placing the orthogonal arms of the dipoles on the top of each other, they are offset by a certain distance. Now, the instrument has proposed science cases of studying exoplanets by looking at the auroral emissions and magnetars, etc., or like and searching for Jupiter-like planets. But it also has another case, which is hydrogen cosmology, is to looking at the dark ages of the universe. And as you know that going to the moon, you get rid of the atmosphere and you get rid of the RFI, so things become easier. But because of the design, there are some limitations. So this design was chosen because it was significantly easier to deploy. That there would be a main module, and out of these modules, you will have 4 rovers coming out, and these rovers will go in zigzag pattern to lay out these antennas, just like you can see here. So this is like a fairly easy deployment strategy, but otherwise, there were like other proposals, but none of them are feasible given the current technology. So, but because of this offset, it can affect the imaging performance of the instrument. So my study actually involves understanding these effects and whether we can actually correct for it in the post-processing of the data. Another project we have proposed recently is to solve is for a project that would solve the main issue of the foreground contamination that we see in the 21 centimeter experiment and the interferometry. So the project will aim at multi-tiered mapping of the diffuse sky and doing a power spectrum measurement. So what we want to do is that we use the ARTFAC instrument to make full sky maps of the diffuse emission, as well as the secondary level measurements that would make diffuse maps of small regions of the sky. And then we have complementary LOFAR surveys that would provide high resolution. And this we want to do in a broadband frequency range. For example, we start from 30 megahertz all the way up to 200 megahertz. That covers from like end of dark ages to all the way to end of the reionization. This we are aiming to solve the problem of the foreground emission, which is like the key problem in the 21 centimeter experiments. So just to provide a summary, the field itself is a promising avenue, and then these 21 centimeter experiments have been at the forefront of the cosmological research, like around the globe. Pretty much like all the big countries are involved, and so much is happening in the field. the detection of the signal itself is expected to unveil a plethora of information, starting from the first stars, probability of the first stars, galaxies, mini quasars, onset and the end of the reionization, cosmic dawn. However, these instruments are limited by the scale of the problem, observational challenges. So most of the research right now in the field is focused on figuring out these problems and solving them. That comes into like that actually itself is a big thing, big field, because you need expertise in engineering, how to design the instrument. You need expertise in signal processing. You need expertise in astrophysics, understanding astrophysical processes. You need expertise in statistical methods and so on. So it's like a lot of things you learn, and there's like the journey itself from going from the raw data to the actual measurement is the most exciting part. Not just the end goal, of course. End goal is that's the key, but the journey itself is amazing, and that's where I've been working on mostly. And there are like exciting times ahead. The SKA is coming up, which is the largest radio telescopes on the Earth. So it will be online later this decade, we hope. And there is also a space and lunar missions planned. So as I already talked about DAPPER and Farsight, they were NASA funded. The European Space Agency is also funding some missions that are going to be in the lunar orbit or on the far side of the moon. So very, very exciting times. Okay, so this was mostly the science part. So maybe we can also talk about a little bit non-science. So let's talk about that. So okay, I was asked to add my journey for how I actually reached here where I am now. So just to give you a summary, I actually hail from Delhi. So, and I chose science instead of engineering. So quit IIT, went to IISER, and also graduated in 2014, and then went for a PhD at the University of Groningen. And I graduated 2 years ago, and right now I'm doing my postdoc. It was like there were a lot of challenges I had, because I think I was not like very lucky when I was applying for PhDs. I got so many rejections, and then eventually the best part is the position that I got was something that I really wanted to do. I did not realize it at the moment, but later I thought that that was probably the best decision, that I actually accepted this position. And it actually not just like I did not just learn about astrophysics. I basically, for the first year, I was learning about engineering stuff. For example, understanding electronics of the instruments, understanding digital signal processing, statistical signal processing, and so on. So this is not something that we study in IISER. Of course, there are like, you do see some parts, but it is not taught as a subject separately. So this is something that you learn as a part of some courses. For example, like a lot of statistical techniques you would see in statistical mechanics, quantum mechanics, etc. But you are not, you don't study them individually, like separately. And the best part, one of the good parts of my PhD was that I was supposed to teach a course, like teaching assistant. And I chose a course which I never studied. It was statistical signal processing. Of course, I was familiar with least squares, so maybe maximum likelihood, but I never studied that course. So I would actually go and attend the classes and then go home, prepare homework assignments, solve the homework assignments, and then hand over those to the students to for that. And then also made also designed a project, same thing from the scratch. So that was like very interesting. It does take you a lot of time, but yeah, it was fun. So yeah, moving on, maybe a bunch of questions like, why did I choose radio astronomy? I like challenges, and like from the start, I worked, like I asked Jadid sir when I was like finishing my second year, okay, I want to do something in astronomy, but related to electronics. So he said, okay, Jad, please, you can try making a radio telescope. And then I think that was the beginning of, I sort of got into this field. And then I started learning new stuff. I went to UT to understand how the UT radio telescope works. I went to NCRA for summer internships, new things learned. And of course, like being an astronomer, you travel a lot. So astronomers are like famous for organizing conferences in like fancy and exotic locations. Like, and trust me when I say fancy and exotic, I'm talking about like Mauritius, Galapagos Islands, South Africa, tropical Australia, and these places. So it's just fun. You get to travel a lot. And sometimes like during my, like when I was applying for PhDs, so I've seen this trend that people always like try to apply for these prestigious universities, but I say that it is not exactly the place. It's the people who you work with. Mostly, like it's the group where you are working with whom you're working. That is the most important part. If you have like a nice group and then people are nice and they are really good at what they do, it doesn't matter what university you are at. For example, you can end up at MIT, and then if the group is not good, then you will suffer the same. It doesn't help. But if the group is good, if they're well known, if they're doing like top class research, then that's you go for, not just the place. And in an honest opinion, academia is difficult. I mean, it's really difficult, but there's like a lot of fun. That if you like what you do, it's perfect. But again, it's not all unicorn and rainbows. There have been like, if you want to establish a career as a researcher, then there's a lot of just like publication pressure that especially like universities which are like outside India, they have a very different kind of functioning. So in order to keep your job, you have to publish. And then in order to keep your job, you have to get money. And in order to get money, you have to publish. So there is a strong publication pressure, which is like, I feel that it's a problem with the field itself, like problem with academia itself, not just like the astronomy. See, okay, your friends are earning who did the same thing, but are at some company, they are earning like almost like twice as you. So you get kind of jealous. Extremely competitive. There is limited job market. And the worst part is there is hierarchical system, which I am kind of, I'm not a big fan of that. So yeah, this is basically it. And I'll stop here. And if anyone has any questions, just feel free to ask.
Thank you very much, sir, for a wonderful talk. Okay, Bagla sir has his hand raised, so you can unmute and talk or ask question.
Yeah.
So given that there are very few experiments which are looking at the global signal, is there any effort to kind of cross-check each other's instruments and data for errors?
So as far as I know, no one has like published, no one has made the raw data public. The Edges group they made their like the spectrums that you can actually get and then try to do basics, like try to analyze. And but I presume that you can like always submit a request. It's like sort of they're open to provide the data, but not like everything. So you would, in the end, you will get like LST averaged spectrums and all, so you can test your own techniques on it. And I do know that Sarah's group has more open, sort of like many other people have actually looked at their data. Edges, I am not like sure.
Okay, thanks.
Are there any questions from offline audience?
Hi, sir. Thank you for the wonderful talk. I have a question which was along the same lines of what Bagla sir had asked. You showed a slide. You showed a slide which showed the current status of the 21 centimeter experience. So over there, you showed some data was accepted and some was rejected, right?
Oh, you mean this one?
Yeah. So like, how would they know that which one is correct and which one is actually wrong?
So yeah, that is the key question. So for example, the edges group published a profile, and they said that okay, we detected a feature, and the Saras did the same analysis. They try to replicate the other instrument like data processing, although the design was different. So like the basic concern in these global 21 centimeter experiments, that your instrument has to have a very achromatic response, that it should not like impose its own frequency response onto what we are measuring. That's why two instrument design choices. And the Saras 3 group said that we did not see anything that resembled what the other group saw. And they claimed that the other group basically mistook any instrumental effect as the feature. So both of the paper are actually like, both of them are like, of course, published, but then who do you believe? So that's why like we need more experimentation on these. Just to figure out. That's why not just these two, there are like bunch of instruments that will like try to do something similar. So maybe it's like since Sarah's group replicated the data processing of what edges did, they did not see it. Maybe if they try something somewhat different modeling, they might be able to see it. This is something I'm expecting that they are working on right now, because they have a lot of data. So they are working on finding out a different shape of the signal. I mean, it might be that they find something else. So, and so the only way you would confirm this, that if everyone comes and say, okay, yeah, all instruments detect the same thing, then you say, okay, this is the right way. But if every instrument is seeing something different, then you don't know which is the correct one. So I think the future would be to wait for other instruments to perform similar tech analysis. And if we start seeing same things again and again, that means that we have detected the signal.
Okay. Thank you, sir.
Hello, sir. We talked about the various proposed projects in this talk. So could you talk a bit more about the square kilometer array and how it's better than our existing models, or how it's supposed to make our readings better?
Okay, so the way these interferometers works is this, that every antenna or every receiver has certain area. We call it as a collecting area, and that's, I think, that is the key fact. That is the main parameter that defines the sensitivity of an instrument. For example, let's say you have an instrument that is only with 10 antennas. An instrument would have its own noise temperature or its own noise. So if you are trying to, let's say, measure a source which is like fainter than its noise level, then you won't be able to see it in one go. But then in that case, you have to like add more and more data to get to decrease that noise level, so that the source become brighter than the noise. So this is what we call the signal to noise ratio. As the signal to noise ratio go higher, you start to see any sort of features in your data. With SKLO design is to be it was proposed to have area of like 1 square kilometer area, a collecting area, but because of cut down, it's actually half kilometer now. So that actually itself is almost 8 times as more sensitive compared to LOFAR, just on the basis of collecting area. As well as the design, the size of the telescope and the baselines will provide similar level of resolution that what we expect with what we see with LOFAR. So these kind of choices make SKLO a few instrument of the future, and it will measure a much wider frequency range. So it will start from 50 megahertz all the way to 350 megahertz, and that's basically you are covering from cosmic dawn to the end of reionization, maybe some of the post reionization part. And then there are like some instruments, for example, Hera is specifically designed to do 21 centimeter power spectrum measurement. It cannot do anything else, basically. If you look images from the Hera, they look horrible. It has a poor imaging performance. The only design choices they took was just to make sure that we get to measure the signal, and we won't want to do anything else. SK is going to be the world-class observatory. So their design is such that not just 21 centimeter cosmology, you can also do other things, like you can detect pulsars, you can detect exoplanets. So many science cases connected to it. And since, just to give you a number, LOFAR has, let's say, around 60 stations, and each station has around 48 receivers in the high frequency band. 48 receivers per station. SKA will have 256 receivers per station, and there will be like order of 500 stations. So that's a lot of antennas. And these are designed to be much more sensitive than LOFAR antennas. So that's already a factor of 10 increment. So this kind of design will help SK to do to reach to look for much fainter signal, which other instruments cannot do. Does that answer your question?
Yes, sir. So one more question. So all these experiments, they involve a certain amount of engineering and instrumentation to them. So for somebody who has done a lot of theoretical stuff and hasn't really been in the field, so how does one sort of get used to it and deal with it?
Yeah, that's an understandable question. For example, even during my master's project, of course, like I did work with instrumental, I did work with instruments, but it was all in theory. I never worked with the data itself. There is a learning curve to it. If you are dealing with the instrument and if you're dealing with the data, there is a learning curve, but eventually you get to it. It's not just that, okay, if you have done theoretical stuff that you cannot learn observing. You can. It's just there is some learning curve, and then you have to understand some level of signal processing and some level of statistical techniques. Yeah.
Okay, sir. Thank you.
I think we are running a bit late, and we are late for Anshuman's talk. So maybe would it be fine if any of the audience has any question, and if they contact you through mail, maybe?
Yeah, that's all right. Yeah.
That would be great. So if anyone else from the offline or online audience has more questions, then they can contact sir through mail. And with that, we will move on to the next talk by Anshuman Acharya. Bharat sir, can you please? Yeah, okay, great. So I will invite Komaldi from MS18 to introduce Anshuman. Yeah, great.
Yeah, hi everyone. Yeah, so we had a really nice talk now, and now we'll be moving forward to our next talk. Hi, Anshuman.
Hello.
Yeah, so Anshuman will be talking about cosmic reionization, the search for an elusive signal. So a little bit history about Anshuman. He's from MS16 batch. Most of you would be knowing him. Anshuman graduated from IISER Mohali in 2021, being among the first graduates to receive a minor in astronomy apart from majoring in physics. He's currently a first-year PhD student at the Max Planck Institute for Astrophysics at Garching, Munich. At MPA, he is a part of the LOFAR Telescope Consortium and shall be contributing towards epoch of reionization studies using the 21 centimeter line observations. He will be talking about the same in today's talk. At IISER Mohali, he did his master's thesis under the guidance of Professor Kulinder Pal Singh. He had been an active member as well as the former convener of the Astronomy Club. It is a great pleasure to have him with us today. With that, I would hand it over to Anshuman. Yeah.
Thank you. I'll just share my screen. Just a second. Yeah. All right. I hope I'm audible as well as
yes,
screen is visible.
Yeah, it is visible.
Okay. Yeah, great. So yeah, thank you for the introduction. and like mentioned by Komal, I'm Anshuman, and I will be talking about the cosmic reionization, the search for an elusive signal. And this is sort of based on something that I've been working on for a little over 6 months now. And that's why it is fairly new. Like we just heard from a previous speaker, there's a lot of interesting stuff going on, and even I'm learning, but it is still very interesting to talk about it. Anyway, like to start off, I'll just share a bit more about me before we go into the talk itself. As mentioned, I graduated from IISc last year with a BSMS in physics with an astronomy minors. The astronomy minors program was actually very new. Like we are the first batch to graduate with something like that. And it has been actually very helpful with the courses that we took up, as well as like having a formal recognition of the same has been quite helpful in that in my experience so far. Right now, I am pursuing my PhD in astronomy at the Max Planck Institute for Astrophysics, which is via the IMPRES program on astrophysics at Munich, where there are multiple institutions involved, like the Max Planck for Astrophysics, the Max Planck for Extraterrestrial Physics, the European Southern Observatory, and obviously universities like LMU and TU. So that's definitely a very lively place to be. And that's the academic side of things. As for research, I actually started with working in experimental condensed matter physics, which was my first research project in 2017. And that was very interesting. But obviously, I was interested in astronomy, and that's where I went for my next internship, where I was working with quasars and then like studying how they are observed and things like that. But then again, I was drawn into another project where we were working with the circumgalactic medium, where we were simulating the circumgalactic medium and trying to understand the properties and how they vary. And all that was fun, and that was all astrophysics. But I wasn't really sure if I wanted to do just that. And that's why, again, I had another change in fields within astrophysics. And I worked with n-body simulations of galaxy mergers to kind of understand how supermassive black holes interact with each other, as well as with other stars around them when two galaxies merge. And that was interesting again. But for my master's thesis, I thought that I really didn't have experience with observational data. And that's why for my master's thesis, I worked with stellar X-ray astronomy using Chandra data. And that again was a very different experience. And as our previous speaker noted, we get to learn about statistics and signal processing and a lot of variety of things. But this was at the X-ray regime side of things. But finally, for my PhD, I am working on epoch of reionization studies, which is the radio side of things. And is my work is much more computational and a bit more aligned with the theoretical side of things, which is again a very big change from being from the high energy observational stuff that I did for my master's thesis. But anyway, let's get to the topic itself. So I believe you would have already been introduced to like reionization and things like that, but I will still have a quick rundown through it. So as all cosmic stories start, we start with the very early universe, which was really hot. And thus you would have like, even if when we eventually had protons form and electrons zipping around, they were still too energetic to actually come together. But as we know, things started cooling down, and eventually the first hydrogen atoms and even a little bit of helium and lithium form. And this was called as recombination during this phase of the universe. But we still did not have anything to light up the universe. We had just neutral hydrogen and a little bit of helium and lithium just floating around, which was the dark ages. But eventually we know that we had, like in today's universe, we have stars, galaxies, and so many other things. And most of the hydrogen clouds that we see are ionized. So something did happen in between the dark ages and then the first galaxies forming and this current state of the universe. And what we expect is that during the early universe, there was a time during which most of the neutral hydrogen was ionized, And it continued to be in that state as further populations of stars and galaxies formed. And that time, that era is what we refer to as the epoch of reionization. So that is all a lot of theory that I've mentioned, but did it really happen? And as we have found so far from observations, is that yes, something did happen. Like when we look at the first quasars, the CMB data, everything points to something happening which ionized a lot of hydrogen. And this period ended at somewhere around redshift 6. So yes, that seems to have happened. And what exactly is redshift 6? That is that actually translates to the first billion years in age of the universe, which in other words means that the light that we are looking at is 13.8, which is the age of the universe, minus 1, which is about 12.8 billion years. The light has been traveling for that time before we observe it. So we know that it would be that what we observe is very, very ancient, and looking for that is going to be very difficult. But that does not stop our curiosity. We still want to know, like, if something happened, how did it happen? And that's where things get murky. Like, we aren't really sure yet how exactly reionization occurred throughout the duration of this event. And we suspect that yes, that it may be like when the first stars formed, they ionized a bit of hydrogen, and when they came together to form the first galaxies, they ionized a bit more. But there could also be the role of other objects in our universe, like AGN or neutron stars, which could generate high energy events, which can again ionize neutral hydrogen. And if that is the case indeed, we would want to know how do they actually affect the reionization duration, and how exactly did it proceed. And those are things that we have no answers to yet. And we also would obviously want to know that after this hydrogen was ionized, how exactly did structure formation change? Like, how did the galaxy formation change during this period? And for finding these answers, like we would obviously be looking for the neutral hydrogen and how the observations changed over time. And that's where the 21 centimeter line of neutral hydrogen kicks in. And that's exactly what we are trying to observe. So that is the problem, that we are trying to observe signals from the epoch of reionization. And now coming to the other side of the problem, which is the problem solvers, which is from which I would be one of them. And I had experience in astrophysics. Like I mentioned, the astronomy minors coursework was excellent and provided a strong basis, and obviously the variety of research experiences. And I had experience in coding. Like I knew how to run small simulations, and as well as perform data analysis from techniques I learned via my projects, as well as the coursework involved. But and this is important, and I wanted to add this just to show that we really often have a lot of learning to do, and we don't always have everything figured out. And that is that I did not have too much experience in 21st century physics and radio astronomy. I had some basics, obviously, from coursework, but it was very rudimentary. And UR studies was something I really had never worked upon. And that's where I started from last September. And it does involve a learning curve, and it does mean that you do not go into a PhD program always knowing exactly what you would be doing. But it also helps because you, from this interaction, from this talk that I'm giving right now, I'm just trying to highlight that you can learn these things as you go through it. So what my work involves here is actually a bit two-pronged. In the sense that one side of astronomy, as usual, is involved with the observational data, where there is signal extraction. So after the data is processed by observers, we try to extract the epoch of reionization signal from it. And a popular technique used for that is Gaussian process regression. And it has been helpful. I will come back to why why it has not found the signal yet, but let's get to it. And the other side is simulations. So we have the knowledge of what kind of physics is around, and we know that, okay, if this is the physics, then what can we expect to see? Obviously, the different simulations have to approximate different things, because actually running the completely accurate physical simulation is very, very computationally taxing. So some simulations approximate some some aspects of it, and other simulations approximate other things. But we get a rough idea of what we expect to see. But there's this disconnect between the observational side and the theoretical side, where the observational side is trying to fit functions and extract a signal out of the data, and simulations are trying to understand what the data would look like. But there's no interaction between them to actually advise the simulation side that this is what you should be expecting to see, and no advice from the simulation side that this is the kind of physics that you need to take into account for your fitting functions. So what I would be trying to do would be to actually connect these two things. And this is important because so far we have while the edges experiment does suggest some detections, but it is contested, and we can say that we do not really have a proper detection of an actual epoch of ionization signal yet. But what we can say is that if the signal is of a particular strength, like how strong the signal is, we can say that, okay, it is definitely weaker than this power. Like this is the power that is the maximum limit, and anything weaker than that would be where the actual signal is, because we are not detecting it yet. And I mentioned something as Gaussian process regression, where what we do is we basically try to fit a function to the actual EOR signal that we expect by subtracting everything else that is there in between. So what exactly is this? Without going into too much detail, I would say that the Gaussian process is basically a normal distribution of f of x values, which are like if you have x1 to xn as your as a variable. In our case, it is frequency. Then how does the power of the signal vary with each value of x? So in that case, we define the Gaussian process as a normal distribution, which can be completely characterized by the mean values of these x. Like you could have an x value which can vary anywhere here, and we take just the means, and as well as the covariance of the x's with each other, which means that if our x here at 1 takes the value of 5, then does the next value of x that we have actually go higher than 5, lower than 5, or stay the same? So if it goes higher, we have a positive we have a positive covariance developing, and if it stays the same, you have 0, and things like and we basically quantify the entirety of the covariance matrix like that. And using all that information, you can get a function out of it, and what kind of functions you use to basically characterize your signal is governed by these values of the means and the covariance. The means obviously are something that you cannot really control, they are the mean values, but how do the different values of x interact with each other is defined by the covariance matrix, and that's something you can control. And that's what we try to do. So what we do here is that if we have a signal y, like we have this data, then we define it that we have some f of x of the EOR, which is the signal we want to see, which is the epoch of reionization signal that we are like trying to find. And then we have the foreground, which is that if there's anything between the signal and us, because the signal is coming from really far away, because going back in time is the same as going further away in terms of redshift. So there's a lot of things that can come in between us, like stars, galaxies, dust clouds, anything. So we try to characterize that as well. And lastly, there can be noise. So we obviously have a noise component. And like I mentioned, we are, because we do a Fourier transform of the energy received versus time data, we have a power versus frequency dependence here. And that's how we go ahead with it. And we are trying to fit specific functions for these f of x values here, and see that and say that, okay, this is what will quantify our signal, and depending on the properties of the parameters of the function, we will be able to say something about the physics of the signal. But again, like so far I've just been talking about fitting functions, and that doesn't really connect with the simulations, and that's what we started out with. So one of the ways to connect the simulations with observations is that like we can get mock observations. That is, like if we do have real observations, and there have been papers published like the about 10 nights of observations of LOFAR data at redshift of almost 9, which already exists, and this GPR technique has been applied to it, and that is excellent. But what if we had 100 nights of LOFAR data? Like that's 10 times more data. And that sounds great, because the benefit is that we would be improving the signal to noise ratio by a lot. But the drawback is that every time you are increasing the amount of data you collect, you are introducing more and more systematic errors, and you cannot really quantify them immediately. Like from night to night, things can change. There can be different sources of noise which were not there in, say, for your first 10 nights, but for your last 10 nights, they flare up. So while the LOFAR is collecting data, actually processing that data to make it reasonable enough to apply this signal extraction technique is a very big process. So if the entire goal is to see like how well is Gaussian process regression working as compared to what we expect it to do, then we can really do the same with mock observations, which is we use simulations to generate what kind of signals we expect to see of the epoch of reionization, and then try to extract that after we like create a mock observation out of it, that we put errors on top, we put foreground on top, and then try to get back the original signal. So this is what I started out doing. And as a proof of concept, we first tried to mimic what was done for 10 nights by one of like my collaborators, which is also mentioned by the previous speaker briefly about when he talked about LOFA, was the Mertens 2020 paper. So they had 10 nights of observations. We had a noise value of what the noise values would be if you actually had done actual observations. And we had these simulated data of the epoch of reionization signal from different kinds of simulations. One of the simulations was the 21-centimeter fast simulation, and we noted that immediately that for example, here we use wave number instead of frequency, but it is more or less the same way of representation. And we note that at the lower values, it is higher than the signal, and at higher values, it does mostly stay lower than the signal. And we also note that we have huge error bars, but that is understandable given that our signal is basically much lower than the noise. So detection is not going to happen. And we also do a similar thing for with another set of simulations called the Grizzly simulations. And we see here that for the same low values of K, it is much lower than the actual signal. But again, it is lower than the noise, so it is expected, and we have huge error bars. And there's something interesting, and that is that if you take the most conservative estimate, that is the highest amount of power that is possible for your epoch for reionization, that definitely goes higher than what we expect to see, but it gives us an upper bound, which is what exactly was done by the actual observational data as well. They gave us an observational upper bound of about 5,000 millikelvin square, where millikelvins are a way to represent the power or the brightness. And in our case, with simulated data, we are showing about 1,000 millikelvin square, which is pretty good. Like we are not still detecting the signal, but we are actually reducing the upper bound. And we know that, okay, like if we are using mock data, we are able to kind of get similar results. The reduction that we see, it could be because that the kind of foreground we are putting on top, or the kind of error we are putting on top, is not enough to quantify the kind of actual errors and that we see in real observations. But still, there is an agreement. So next, what we can do here is to move on to 100 nights of observations. And that's what we did. And that's where things get interesting. We see that reduction of the noise doesn't really reduce it by too much for the 21-centimeter fast simulations. And the results that we get overestimate the signal by a lot. But in the case of Grizzly, we see that the actual signal is now stronger than the noise. And thus we expect that if this was the kind of observations that we get, if we look at the sky for 100 nights, we would be able to extract this EOR signal, But by applying GPR, we are seeing that it misses it. It has too small error bars, and it is going below the signal. And it basically, if you are again quoting upper limits, it would mean that it would completely miss out the upper limits for the actual signal, and the data that the results that you present, the physics that you get out of it, would be kind of bogus in this sense. So increasing 100 nights, we thought it would like an increase in SNR would be excellent, but it didn't really do much. And as you would have seen by now, we are using different simulations and we are getting different results, which is a worry. Like, you do not want that. You want that like all your simulations, despite their variation, should give you something that is similar, or at least the signal extraction should work in a similar way, even if the signals are different. So one of the reasons that has been quoted so far is that the fitting functions that Gaussian process regression uses assumes that the small biases, like say if the fitting function misses the signal by a certain amount, then it's okay. But what was noted was that even small variances, variation in the covariance matrix that is used for those fitting functions can lead to very different results. And these small biases, which like when there have been papers which quantify them, showcase that they are smaller than what is the current acceptable limit for the fitting, like for the best fit equations that we are using. So maybe that's the reason that the GPR is not really a good way to fit the functions to the data, and thus trying to use that to recover signals is not going to work. But if that's the case, then there should be a workaround to it. And that's where we bring in the second use of simulations. In other words, what we are doing with simulations next is that we are generating a large set of simulated data sets, and we are feeding it to a deep learning algorithm. This, what it does is that it generates a more physical fitting function, because it based on the variation of the different kinds of data sets that we put, like if in one set of simulations, one of the parameters, like for example, how fast the ionization is occurring, which is the ionization efficiency in some sense, if we are changing it slightly, then even that is being taken into account while defining the more physical fitting function, which learns from this deep learning algorithm. So in theory, this should work. Like, we should be able to have this deep learning GPR model where we are able to extract signals more physically, and it also agrees with what our simulations say. But this is not something that has been robustly tested. Like, so far, we are at the first step, which is that we are using 21 centimeter fast, one of the simulations I mentioned, to train the algorithm with thousands of simulations. And then we are testing it with mock observations from the same simulation style, which is the 21 centimeter fast program. But because of the differences with the different simulations, it makes sense to go to the next step. And that is that if we are training our algorithm with the 21 centimeter fast simulations, then maybe we should try some other simulations, like the Grizzly simulations, for testing it. Or maybe the vice versa, train it with Grizzly and test it with 21 centimeter fast. Or train it with both of them and then try to test with both, like test with each of them separately. Those are all the different kind of things that we are currently working on, and that is we do not have the results yet, and that's where I would have to apologize, because again, this is a work in progress and does not have all the results together. But the main question that in the end people would ask is that after doing all this, after training your data sets, spending a lot of computing hours generating these simulations, does it really improve our results with the plain vanilla GPR that we actually used? And that is the biggest question, because in the end, if you're trying to sell people on an improved technique that you have developed, you'd want to show them that yes, this improves upon what they already do. And that is what I'm working on. And maybe in the future, I would be able to share more details about how this turns out to be. And that is something that would also require me to learn more about deep learning, about how to apply that to actual data. And lastly, to actually get observational data and learn about how to reduce systematic errors and get 100 nights of data and see if we are able to actually do the things that we claim to do. But anyway, like after this, this was all about work. It was suggested that I should also talk to you guys about maybe some advice or something that in general that in hindsight I understand. And one of the key things is obviously practice programming right from the start. If you're interested in astronomy, because if you go into data analysis or if you go into simulations, everywhere you would need to learn programming. And the more you learn about it, the faster you learn about it, the better it is, because you get to know about all these techniques and all these different ways that you can work with in this field. And yeah, when I say programming, it is not just limited to just tapping away on the keyboard, because there is a lot of math that also goes in, like the numerical methods or differential equations, or even just general statistics. And all of that is important, so do not neglect that. And I will also suggest that if possible, do push for more electives in statistics and something, because like even the previous speaker noted, like that's something we do not learn yet, and if you do get to learn it, that's definitely great. And as you would have seen from my previous research experiences, I tried to explore different fields, because when I came to IISER Mohali, the only thing I knew was that I liked astrophysics. I did not know what exactly I liked in astrophysics, and I did not know that if I started working on a project doing something related to astrophysics, like say studying quasars, did I really want to stay just studying quasars all my life? So I would definitely suggest that if you are not sure about it, do explore. But yes, however, there is always a clause and a terms and conditions attached. That is that if you are actually switching between specializations, then at least try to note down what are the past experiences that you have, which will make it easy for you to transition. Like if you know a certain amount of programming, then how can it be translated to going from one field to the other? And that is something that actually helps you in the long run as well, because this is what you would be doing even in the future. If you, for example, if you go for a PhD and then for a postdoc, it helps if you are able to branch out a bit. Like if you are applying for a postdoc and you know that, all right, I want to do something else, then that increases the amount of options that you have. Or if say you do not want to go for a postdoc, you want to go for a non-research job, then it helps to be able to identify what kind of skills that you have, which can be translated from your current research to something which is not involved with research. So I think that is quite helpful, and it does mean that you would have a certain amount of introspection, but there's no harm in that. And yeah, like I said, push for course in statistics and maybe in other fields of astronomy and astrophysics as well. That may mean that the institute would have to hire more people, and that is a difficult process with a lot of admin issues involved. But yes, like if you showcase interest, the institute would definitely recognize that and eventually act upon it. Like for example, the astronomy minors program was something that did not exist, and but when it was first like discussed about, the people in our batch and even some seniors showed quite a lot of interest, and that I believe was definitely instrumental in paving the way, because if there was no student interest, there was no point in introducing it. And just because students were interested, it meant that more courses started being offered to make it a realistic option as a minor. And lastly, obviously, like don't forget to have fun, like talk to your friends. The amount we learn from our friends is incomparable. Like even if it's just a random discussion, there are a lot of things that you can learn. And it doesn't really mean that you can make friends with just the toppers, because there are a lot of things that you miss out if you are not getting different perspectives of a topic. So just don't like limit yourselves to academics or things like that, and talk to your friends, spend time with them, and it will be helpful. So yeah, like I would like to cut it short so that we can have more amount of questions. So if there are questions, like we can go ahead with it.
Yeah, thank you very much, Anshuman. It was a very well explained talk, and I personally could follow it throughout. Bagla sir has a hand raised, so
yeah.
Hi, Anshuman. I
Hello.
hope you are doing well.
Yeah.
See, a lot of effort is being invested in using machine learning for this kind of work.
Yes.
One question that I have is, have we kind of given up on developing physical insight and taking that route? Or is it just a quick and dirty approach where we throw a lot of computer time on the problem and hope that ML will give us some answers and then we'll learn things as we go along? What is the thinking?
Yeah, so the thinking is like, this is that's a very valid point, and it is kind of true, like what you say. So what we do have is that people are seeing that we have simulations, they are running, we have data analysis techniques that are there, and they are not able to connect it. So yes, like at the moment, like what we are doing right now is to see if throwing machine learning at it works, and does it work efficiently enough to actually like validate the implementation of so much computing time on it. So there was no like there can be different other ways to connect your simulations, which people claim to be are more physical, because we are starting with certain physical parameters that we are sure about, and then trying to evolve simulations out of it. So if we cannot find any other way to connect it to how the signal extraction techniques work, one of the suggestions was that if there's nothing works, try machine learning, and that was what people were trying about. And but what I have been doing is basically questioning that, basically saying that, is it worth it? Like, after doing all this machine learning, how much of an improvement do we get? So if we don't get much of an improvement, we will basically chuck it out. But if we do get improvement, we have to then understand that what exactly was the changes that we made to the signal extraction technique when we implemented machine learning, which made things work better. And again, it is a kind of a circular loop, because when we say working better, we are saying that we are able to extract signals better, and we are again like at the moment just working with mock data. So again, we are going back to simulations and saying that yes, we applied a technique based on simulations to extract data which was from simulations. So there is a lot of tricky things involved, and that comes because we do not really know what kind of signals are out there, but we are working on it. And this is, as you said, it is basically something that we're throwing at the wall and seeing how well does it stick, basically.
Okay.
Can I pitch in a little bit on this?
Yeah, Bharat.
Oh yeah, definitely.
Yeah, so this is what I understand. So this has to come to this basically boils down to the philosophy how we are measuring the signal. So there are experiments that try to, let's say, avoid foregrounds and just look into the region where you only have the signal, like UR window, and then like average the data as much as possible so that you beat the noise, and then run simple MCMC and then find the signal. We don't know what kind of physics there is. Like the key question is, how do you know whether you actually had made a detection? So that's one of the key points. When we come to the point of subtracting foregrounds, that's the big deal, because how do you know whether you are actually not subtracting the signal by itself, whether you are just like subtracting the foregrounds? But with machine learning, what we are trying to do is we are trying to find out like the optimal Gaussian process that is that can represent like tens of thousands or maybe like hundreds of thousands of physical models with a more simple function that you don't need, like for example, if there is some other like if there is some extreme astrophysics going on, then sometimes your like basic guesses about like these Gaussian processes from certain simulations won't work, or from a certain point of view. So that's why I think the use of machine learning comes when you are like trying to understand like a wide range of these physical models that are possible, and find out an optimal sort of Gaussian process kernel to represent the signal in your data. So I think that's what I
yes Yeah, so like that is what like it is one of our common collaborators now, Florent. He's implementing that. So I would basically be a part of testing it with a variety of mock data and seeing how well it performs. Yeah, so it is still like there's a lot of testing to still be done, and it is something we are working upon. And maybe in a few months we would have a bit clearer picture about the technique itself.
So does anyone from offline audience? Yeah, you can come.
Yeah, so I had a question regarding the deep learning model that you are using. I would like to understand what sort of model exactly is it? As in, when you say that the model will output a function, you usually the machine learning models that we see, they output functions which are complicated exponentials compounded with other exponentials and polynomials of these. And the exponentials argument may itself be a polynomial, a typical neural network, for instance. Now, this outputs a function. So generally, when you have signals, you will have something like a power law plus a Gaussian plus something else added to it. So I would like to understand how exactly can a deep learning model sort of give you a function of this form, which is the sum of power laws and other such simpler functions. And why can't this such a fitting simply be done with the traditional methods? Why do we need something like deep learning for this?
Yeah, so like there are, okay, we'll go by one. So firstly, like what the deep learning algorithm is, like it's like you said, it's a very general thing. It uses a variational autoencoder. So you feed in a lot of information and it tries to give you an output by limiting what is the latent space, like what kind of what are the key features that it wants to keep, and then you kind of try to find a resultant out of that. And yes, like the result, what we are in the end doing is that from the resultant, like if you look at the power spectrum of it, then we have like an averaged value of results. And the function, actually, I also have to go back and see like how exactly does it get the function right. But so far, like, and it is very complicated. Like the function we use are called the Matin class functions, which like we generally use with GPR, but we are slightly altering that for when we use deep learning. So it makes alterations to that in the to that function. But how exactly it's doing it is something that I will have to also look into, because right now I'm just working with how to implement that successfully. And whether it is implementing successfully. So we are on the I'm on the testing side of it. But anyway, like what I talked about was that the basic Gaussian processes is the general plain fitting way of doing things. Like, so we have already tried that, and there are limitations to it. Like if we are changing the mock data from one, like instead of using one simulation, we are using another, we are facing problems with that. And that means that if our physical signal, the actual observation, is not how we expect it to be, then there is a very good chance that we will miss detecting it. And in such a situation, we are basically trying to understand, like, if the physics is slightly different or very different, then how exactly would it change the kind of data we see? So for that, we are implementing deep learning. Like what Bharat also mentioned now, we are kind of trying to see a large number of models and try to get a common picture out of it, which can then be implemented. Because the basic fitting that we are trying is missing things. And it has been quantified that there are biases which can explode into completely missing out the signal if we use the current fitting functions, that fitting methods using just Gaussian processes. So right now that has been implemented with observational data, the Gaussian process regression is basically without any deep learning or anything. And now we are just testing that whether the deep learning thing is actually helpful. And once it actually turns helpful, we can then maybe apply it to real data and see what we get.
Thank you.
So I think we can move on to the next talk if there are no questions from audience. Okay, there is Shashwat Saurav. If you
Okay.
unmute, then you can unmute and ask.
Yeah, hello, sir. So, like
Yeah.
you mentioned about creating these fitting functions. So,
Yeah.
there might be some instances when you might run like there might be overfitting and underfitting. So, like, how do I mean solve it? Like, you keep on generating this mock data and then you see which one fits the works out better
No,
for your model.
no, the thing is, like once we have like right now we just have the mock data in the sense that we are assuming that this is the observations. So once we have it, that is it. Like that's like we do not really make changes to it based on our fitting function, because that's where you will run into biases, because you're trying to change the kind of observations you have to basically fit your data, fit your fitting function. So that's not what we are doing. What we are doing is that given any set of observations, if we have these kind of fitting functions, what are the kind, like, is it really working that well in getting back our signal from the mock observations? So yes, there can be cases of overfitting and underfitting, and that can cause issues, as we have seen so far. And what we are trying to do is kind of eliminate that. And it is definitely a case of underfitting, actually, because we are not detecting the signal just yet. So we, or maybe we are missing it out. So to basically improve on that is why we are introducing deep learning, and we'll have to see how that turns out to be. But yeah, like we are not really changing the mock observations for the fitting function. The fitting function is there. We are just and the mock observations are there. We're just trying to see how well it matches.
Oh, okay. Got it. Thank you.
Are there any questions, more questions from the online audience? Okay.
Yeah, if they have any more questions, they can contact. So that's fine.
Yeah, great. So
Okay.
thank you very much, Anshuman, for this very exciting talk. And we hope to come back to you when you get the results and sort of bridge the gap between the cliffhanger that you have left us at. And thank you very much. With that, I would like to go with to move towards the last talk of today's second session of Jahanvi. I would be introducing her. Jahanvi, maybe you can switch on your camera. Yeah.
Hello.
Yeah, hello. Great. So the title of this talk is B Stars. Jahanvi graduated from Aiser Mohali in 2020, majoring in physics. She is currently a first-year PhD student at University of Liege, Bologna, Belgium. She's working in high-energy astrophysics, mainly on the high-mass stars. In today's talk, she will introduce the B stars and their general and observational properties. It is our great pleasure to have you here with us. And with that, I would like to hand over to Jahanvi.
Thank you so much for the introduction. Can you hear me? Because I want to see if this is audible.
Yeah, you're audible. Yes.
Okay. Thank you for the invitation, and thank you, Prajakta, for the lovely introduction. Let me share my slides. I hope you can see the slides.
Yeah, slides are visible.
Okay, thank you so much. So, hi everyone. Today I will be telling you about BE stars. It's just a general talk and not actually the work which I'm doing, but I'm working on BE stars. So let's begin with the stars itself. So stars. I want to say something. So don't kill me, but I will say it. Do you know what are stars? Stars are the motivation of every student who come into astronomy, and then they will end up working on codes. Okay, jokes apart. So stars are self-luminous celestial bodies, and they are classified on the basis of the temperature and the luminosity. So as you can see in the first diagram, that we have O-type stars and B-type stars and all the type of stars, and O-type stars are the hottest because the surface temperature is higher for them, and the M-type stars have lower surface temperature, and that's why they are the coolest stars, right? Down below, we have the HR diagram, the very famous HR diagram. We have luminosity, which is in the terms of solar luminosity, and it's increasing towards the positive y-axis. And from left to right, we can see that the temperature in Kelvin is decreasing. So you can see that this branch is a main sequence branch of the stars, and here we can find a very big number of stars because stars spend most of their lifetime in the main sequence phase. And then we have supergiant stars, giant stars, and the dead stars, which are known as the white dwarf stars. What I want to say is that depending on the temperature, there are different elements that get ionized, and therefore we can see them in the spectra of different kind of stars, and that's how we distinguish between the different kind of stars. So I will mainly focus on the B-type stars because BE stars are the B-type stars. So you can see that in the B-type stars we have hydrogen lines, but we don't have ionized helium lines. Although recent studies do find that in early B-type stars we have ionized helium lines, but generally we say that this is the distinguishable feature of B-type star from O-type stars. One more thing that one should see from this spectrum is that for the hot type of stars we have more lines on the blue side of the wavelength, and for the cool stars we have more lines on the red side of the wavelength, and that's why we have this color coding here. So moving on to the B-type stars, B-type stars are 2 to 18 times massive than the sun. I'm sorry but I think that this is the rough range that I should take, because I see some stars which are 2 point something, and I saw some stars which are like 17 point something. So I took like 2 to 18 as the mass range. Some of the B-type stars show anomaly behavior in the sense that they show different ionized or neutral lines. So for example, in helium strong stars, you can see the neutral helium lines and very strong magnetic field. In helium weak stars, you saw strong hydrogen spectra with understrength helium lines, which are weak helium lines. Mercury manganese stars, you can see ionized mercury lines with different manganese lines and all, and we do have weak magnetic fields here. We are talking about BE stars. So BE stars are the stars which show emission lines in their spectra, or I mean emission Balmer lines in the emission spectrum. So let's talk about the classical BE stars. So the widely accepted definition, I would say, is first given by Jaschuk in 1981, and then there is a small correction that is done by Collins, but it's a very important correction actually. So it says a non-supergiant B star whose spectrum has or had at some time one or more Balmer lines in emission. So basically, the correction that made by Collins is the Balmer lines, because it was by Jaschuk in the Jaschuk definition, you can see that it's just emission lines in the spectra, and then he called that no, there are Balmer lines. They are essentially the Balmer lines. This definition excludes all the stars which are B-type stars and which show emission line, they show emission line, but they include all B-type stars with which have the density material greater than 10 to the minus 13 gram per centimeter cube. And this the only problem is that it includes all main sequence B-type stars which show emission and which have so much density. Obviously, why this density range? Because above that you will have the circumstellar material around the star. There is no way that you don't have it. So the only problem is that it do not take into account the physical mechanism by which this disk is formed. So just to make sure that we understand the difference between, and we can distinguish the B-type star and BE-type stars, just looking at their spectrum, you can see the Rigel is a very well-known B-type star, and it is in the Orion Belt constellation, and you can see the absorption line in the spectra. Whereas if you see the Gamma Cas, which is the very well-known and very well-studied BE-type star, I want to make one point that Gamma Cas is first discovered in 1866, and it is that discovery of Gamma Cas in which they saw the emission lines and they said, oh, this is not a normal BE star, it's something else. And that's how we have different classification of BE stars. So it is the first BE star that was came into the picture. And you can see that we have emission lines, so very strong H alpha emission line, and then we have H beta emission line also. So what are the properties of BE stars? Sorry, classical BE stars. It's important to say classical. So classical BE stars, they rotate very fast. When I say they rotate very fast, it means that their mean rotation rate is around 70 to 80% of the critical velocity. By mean rotation rate, I essentially means that we took a large sample of BE stars and we are just we see the histogram and we say, okay, our mean rotation rate should be this. So it's just the mean value, and which means that most of the stars do lie in this range, but we do have stars which are slow rotators. And we do have stars which rotate like 90% of the critical velocity. It's like this. Now, the second very most important thing that we should know is that these stars, the BE type stars, they have a circumstellar gaseous disk around them. And most of the line emission that we can see in the spectra is due to this disk. And this emission lines are typically double peaked. Why I'm saying typically and not like okay, these are double peaked every time, because it depends on from where we are looking at the stars. So first of all, let me explain why should we have double peak. So this is the BE type star in the blue, and then you can see that one part of the disk is going away from the observer. So observer is here, and the one part of the disk is coming towards the observer. So we have two peaks from two different part of the disk. That's why we have double peak. But if we see star from the position A, so then the star will look like this, and then we will have only one peak. And then if we are on some inclination from the disk or from the equator, we can start seeing the double peak. If we are on the if we see the star from edge on, we can see some absorption feature also, and that's why we say that BE type stars, when that's why we say that the shell stars are the BE type stars that we can see from edge on. And this idea was first proposed by Struve in 1931. He said that okay, these are just BE type stars which we can see edge on. And this idea actually got criticized during 17 and 18 because people proposed some models that were opposing this idea. But like around 1984, one paper came with the interferometric observation, and it said that this geometry actually explains very well the absorption features. So let's talk about the features that we can see in the spectra in the spectrum of a shell star. So we can see the broad absorption lines that are due to the rotation of the photosphere. We can see the emission lines that are from the equatorial disk, or you can call it circumstellar gaseous disk, or you can call it BE disk, anything you want to call. And and we will have the narrow absorption line that is produced due to the fact that we are looking at the disk from edge on. So this diagram is of Pleione. Why I put it? Because it's a variable star. If you ask me question, I will tell you about Pleione star. It's a very interesting star. I'm sorry that you can, if you cannot see the spectrum of the Pleione star is this one, and the spectrum do show the double peak. Okay, let's move on to the rotation, because I said that I will tell you more about the critical velocity. So so BE star rotate closest to the critical limit. It means that the centrifugal force balances the gravitational force. At the centrifugal force at the equator balances the gravitational force. So we say that a star is rotating critically when the rotational velocity at the equator is equal to the Keplerian circular velocity. And due to this rapid rotation, we can study so many things from the BE star population. So we can look at the effect of rapid rotation on the star, not only on the star, but also on its wind density, on different properties like pulsation properties. And we can study more about the traditional theories and traditional approximation. We can validate them. So it's a very good proof for that. Now let's talk about the disk part. So the disk, the BE disk or the circumstellar disk, we also call it decretion disk. Why we call it decretion disk? So you can relate it with the accretion disk. Accretion disks are formed when a compact object or a protostar accumulate material around it, and the decretion came from the fact that here the star is ejecting the material, so the material is flowing away from the star, and that's why it's forming disk around it, because it's highly rotating. So these disks are Keplerian in nature, which means that the velocity of the disk material is varying as 1 upon the square root of r, where r is the distance between the star and the position from at where you are calculating these velocities. And they are also known as viscous disk because they are governed by the viscosity. So just to clarify one point which I wrote here, that they don't have inner radius as such. You can see here. So if we have a BE star, then the inner radius of the disk is just the surface of the star, and it's not like that we have distance between the disk and the star. It's just the same thing. And so what are we expect, or what we can actually observe from the emission spectra? We can see like we can see the equivalent width from the emission spectra. So it's just the integrated strength of the line. We can see the peak height above the continuum, which is like this. I'm sorry, I forgot to tell you to remember this, but this. And then if we have an emission line profile and we want to fit it to the Gaussian line profile, we can calculate the full width half maximum also. Because it is rotating, we can calculate the radial velocity, and we can because we have two emission peaks, we can calculate the height ratio. Now you will say, oh, the width height ratio will different from one, because what you tell us is that we have two peaks which are of same height every time. No, it's not true. Definitely you can see in these examples that the height will vary. And why will it vary? Because of the fact that the density is not uniform of the disk material. So let's see the binary systems of the BE stars. White systems are the systems in which the BE star and the companion is a bit more far away from each other, so they do not exchange the mass between each other. And closer systems are the systems in which we have circular orbits. I will tell you about closer systems in the next slide a little bit more. BE X-ray binaries are generally the system in which we have BE star and a compact object, which can be a neutron star and or white dwarf or black hole. Although we didn't observe any black hole system yet. I mean, they are just candidate, not confirmed black hole systems. For the last point, which is post-mass transfer systems, let's look at this slide. So what happens is this person he proposed the idea that that if we have to explain the rapid rotation of BE star, and it's in the binary system, then the best explanation will be this: that suppose we have a lighter star and we have more massive star, and they are in the binaries. So then the most massive star with time will evolve and it expands and it will lose its mass. It will fill its Roche lobe, and the mass will transfer from its Roche lobe to the Roche lobe of the other star, and then the mass, basically it's Roche lobe overflow. That will happen. After some time, when it will exhaust all its mass, it will either become a white dwarf, either it will go into a supernova and become a neutron star. That's a different story. But what happened to the lighter star is that it gains the angular momentum, it gains the mass. That's how it will start rotating very rapidly, and it will become more massive. So that's how he said that it will be like this. That's how he explained the rapid rotation of a BE star, and also the evolution part of the BE star. So I told you that I will tell you about the closure systems. So basically what happens is we say that if we have a compact object in the binary system, we have more elliptical orbit. But for the circular orbit, if, for example, at some point when it is not, this star is not still a white dwarf or any other compact object, it will just exhaust its hydrogen core, and it is a stripped helium star. And when it's a stripped helium star, it will rotate around it, and it will form a circular orbit and not the elliptical orbit. Why there is a difference? Because during the supernova, this star orbit become more elliptical, and that's how it will move with the more ellipticity. So why binaries are important? I mean, the whole point of telling you the binary system and all this is that binary systems are important in BE stars because they help us to impose additional constraints on the model parameters. So we can say we can pose more theories that, okay, why we have more rotation, why we have the variability in the disk, why we are having this VR variability, which I told you, which is like the two peaks, violet and red peaks variability, and all these things. So it's just for that, it's very important. So I will like to leave you with the take-home messages, and I would like to end by saying that there are so many things that we don't know about BE stars. That, for example, we don't know why we have, what is the main mass loss mechanism. We don't know why the BE phenomenon, which is the formation of the disk around the BE star, how this is happening, how like they are showing shell features sometimes, and sometimes they are not showing shell features. These things are so unclear, but my work is to understand basically the X-ray emission of the BE star using different models. So I will leave you with the take-home messages, and I will take the questions.
Thank you, Jahanvi, for a wonderful talk. Actually, I had one question, and I would like to ask it. So you mentioned about the definition of B stars changing from like just the emission line to Balmer emission line. So does it, I mean, So does it have any specific reason? And also, are there any other type of stars that have other types of, say, Lyman line or something like that? Might be a very naive question, but just the curiosity.
Yes. So they just they changed the definition into this because first because as you can see in the YamaCast, we have a very strong H alpha line. So they see that the most prominent line that we can see are the Balmer lines. So that's why they said that it's a Balmer line. So this change is basically to tell that if we have other line emissions, then we will not consider it as classical BE stars. It will not qualify that. Since you asked that, do we have another type of stars? We do have another type of stars. I mean, you can read about them. For example, you know, this BE stars. People generally confuse these BE stars from these BE stars, but the difference is that these BE stars show forbidden emission lines also, and we will never see that in the classical BE stars. So that was the only point to change the definition.
Okay, great. Does anyone from the offline audience have any questions? Yeah.
Could you elaborate upon your point where you said that a BE star does not have an inner radius? Could you explain it again?
Yes. So basically what happens is that, just imagine, for example, this is a BE star, right? And if we have to take out the material out of it, and that material itself is accumulating around it and making a disk, then it cannot be detached from the BE star.
Right.
So we don't have the gap between the two. I mean, you can have I mean, no, in BE stars, no gap.
So, but I mean, you can still define an inner radius in the sense that it's a thin disk which is around it.
We say that it's a thin disk. For the inner radius, we just take the stellar radius. We say that the stellar radius is the inner radius and the outer radius is the radius until which the disk truncated.
Okay. And also, what is the reason behind the formation of this disk?
We don't know. That's what I said.
Okay. Okay. Thank you.
I mean, it's a very controversial thing. Some people say something else. Some people say something else, and I'm afraid that I will say something which will not be accepted by others. So,
right. Thank you.
Yeah, it's okay.
Bagla sir also has questions, so you can.
Yeah. So good to see you and listen to your talk, Jahanvi. I hope you are doing well. See, the Balmer emission lines, which you repeatedly pointed to, are typically a signature of a photoionization region around a star.
Yeah.
So is there a regular H2 region around these stars, or are these coming from the disk, or is there some outer envelope of the star from where we are getting this? That part was not clear to me.
They are generally coming from the disk.
Okay.
Yes.
Okay. Thank you.
I also wanted to ask one more thing. This particular type of stars, that is B star, seems like a very niche area or very particular area to like work on. So how did you get interested in this field? I mean, were you already interested in this field, or were you offered this topic during the PhD, or anything about that?
No. So what happened is, when I was applying for the PhD, there was COVID, which was very bad. But when I saw this position, it talked about massive stars, and when I inquire about it, I got to know that this is about the study of X-ray emissions from the BE star. And then I read a little bit about it, and I got to know that there are many open questions. So this is the first thing that attracted me. Second thing is that I did my master thesis on X-ray transients. So, and I did read about BE X-ray binaries, but not in very much detail, because I was reading about I was reading about black holes X-ray transients. The only thing that got switched now is I was first working on the X-ray emission from the accretion disk of the black hole, but now I am only focusing on the BE star and not on the binary companion, the compact objectives.
Yeah, that is a very interesting, journey.
Yes.
Does anyone from online audience have question? Okay, so I think we can end this session and also conclude this second session of the symposium. Thank you, Jahanvi, for this wonderful talk and for being here with us today. I would also like to thank all the. Okay, Devang has a question. Devang.
Oh, I stopped sharing my screen.
Yeah,
is it okay, Devang?
Yeah, sure. Okay, I think it was.
Devang was just clapping. He didn't have a question. Yeah.
Oh, thank you.
Okay, so thank you very much, Jahanvi, for being with us here today, and I would also like to thank the audience for attending the second session of symposium and being with us till now throughout the three sessions. We will again meet tomorrow at 10 a.m. for the third session of the symposium, and we hope to see you there. So do attend the third session as well. With that, I think I would conclude this session and end this meeting. Thank you very much.
Thank you all.
Thank you.
Yeah.